welcome back to Master aka tutorial. Today we want to continue on the simple harmonic motion. Here we have the representation of a simple harmonic motion. It is a graph of displacement versus time. Here you have the displacement y, and here you have the axis for the time. The horizontal axis is the axis for the time. Okay, now here is an example of simple harmonic motion. An object of mass m attached to a vertical spiral spring. Okay, this mass m, when displaced downward, when pulled downward and released, will be oscillating up and down, and that oscillation is an example of simple harmonic motion. Okay, now let's say we have graduated the line, that is the displacement line, maybe from 1 2 maybe to 3, here again 1 2 to 3. Let's say the object will be moving up and down, okay, to those position. Okay, now what is happening here is that because the object is moving up and down through the line y, this is displacement y, okay, through y, because the object is moving up and down through y. Let me write it very well. This is 3, this is 2, okay, 1 2 3. Because the object is moving up and down from, let's say, from -3 to -2, from -2 to -1, then to 0, from 0 to 1, from 1 to 2 and to 3, and back down 3 2 1 0, and so on and so forth. So there is a simple harmonic motion. Then this simple harmonic motion can be represented by this formula, the general formula for simple harmonic motion, the general equation of motion. This is called an equation of motion because it represents the displacement, the change of the displacement with respect to time. Okay, so we're going there, we are going to get there, I will explain. When this object is moving, let's say I put it on 3 here, by 3 here, and I release it, it will go up, come back down. So at its going time, will be going with it. I mean, seconds will be going with it. Our clock, at the time I leave it, we start the clock. So the clock is starting from 0. So as it's moving up and down, the time will be going on. Okay, so if we plot the graph of how the displacement y is changing with respect to time, we are going to get something like this, a graph like this. Okay, and this graph is a sine graph. It's called a sinusoidal graph, in the sense that if you look at the if you plot the graph for y is equal to sine x, you are going to get the same shape. Okay, so in trying to determine the constant, that is a, w, and a and theta, we discover that theta is equal to wt. Okay, like I said before, if you try to plot this graph, the graph of y is equal to sine theta. Okay, by the way, let's call this one capital A. Cool. So like I was saying, this is the representation of how an object is moving in a simple harmonic motion, and this graph can be represented through this formula, that is if a is the amplitude, okay, therefore y, which is the displacement, is equal to the amplitude, that is a, times sine wt. W, we said it before, is the angular velocity. Okay, then t is the time taken, and this is called the equation of motion of an object in simple harmonic motion. Okay, we said A is the amplitude. Okay, the amplitude means maximum displacement from position of rest. Okay, uh, maximum displacement from position of rest. Okay, so now frequency. Now, uh, because of this displacement time graph, we are going to talk about some new words, some new terms that are related to simple harmonic motion, and of course also related to rotational motion, because like I said before, they have some similarities. So the frequency is one of them. What is frequency? Frequency is defined as the number of oscillations performed in 1 second. Okay, the unit for frequency is hertz, and hertz is denoted as Hz. Okay, so then we have another word which is also very important: period. What is period? Period T is the time taken by an object for a complete oscillation. Okay, now what is a complete oscillation? Okay, now let's say I pull this object downward and I release it. When the object goes up and come back to the initial position, that is the place at which it was before I release it, then we will say that the object has performed a complete oscillation. Or if the object was up here and goes down and come back up at the same position that where it was, then we say that it has completed a complete oscillation. Or if the object was there initially and goes up, it has to come down and come back at this position again before we say that it has completed a complete oscillation. Okay, so that is the complete oscillation. The time taken for that complete oscillation is called the period T, and it is in seconds. It is expressed in seconds. Okay, in seconds. Okay, so now from these terms and the representation of simple harmonic motion, which is the displacement time graph, we can go on and get some formulas. Okay, we know that the angular velocity is theta over t. So for a complete oscillation, we already said that the time taken is what we call the period, capital letter T. So we can change small letter t by capital letter T here for a complete oscillation. Okay, then a complete oscillation is equal to 2 pi radians, in the sense that a complete oscillation is like a circle. Okay, it's like a circle. Like I said before, when the object is at a point, it goes around and come back. That is what we call a complete oscillation. Like when the object was here, it goes up and come back. It's as if it has done a circle. It's as if it has completed a circle. That is also called a cycle. Okay, so the complete oscillation can be seen from here to here. So that complete oscillation is like a circle, and you know a circle has 360 degrees, and that 60 degree correspond to 2 pi radians. Okay, so therefore we can change this for a complete oscillation. Theta is equal to 2 pi. So when you substitute t and 2 pi in the formula of angular velocity, you now get W is equal to 2 pi over capital letter T. Okay, since the frequency is equal to 1 over T. Okay, we said frequency is the number of oscillation performed in 1 second. Okay, so therefore the frequency is equal to 1 divided by the time taken for a complete oscillation. Okay, so since f is equal to 1 over t, if you substitute 1 over t by f here, then you have an angular velocity is equal to 2 pi f. Okay, so at the same time you will now have, if you use this formula, you make t the subject of the formula, you get t is equal to 2 pi over w. Okay, so that is about this second class on simple harmonic motion. I hope you've liked this, you've enjoyed, you've learned one or two things in this video. If yes, please like, comment, and share. And also don't forget to subscribe. See you in the next video for the last one on simple harmonic motion. Thank you. See you in the next video.